Ancient Egyptians cut granite with a precision that stops modern engineers cold. I want to explain what that actually means, why the old explanation never worked, and what new microscopic evidence now shows. Let me start with the granite itself. Granite is not easy stone. It sits at 6 to 7 on the Mohs hardness scale. That scale runs from 1 to 10. 10 is diamond. 7 is quartz. Granite contains quartz, feldspar, and mica all packed together. Even today, cutting granite with modern diamond-tipped power tools, industrial coolants, and computer-controlled machines is slow, expensive, and brutal on equipment. Every professional who works with it knows this. It resists everything. So when I say ancient Egyptians shaped granite with industrial-level precision, that is not a casual claim. That is a genuinely difficult thing to explain. Here is what the surfaces actually show. Inside the Great Pyramid, the King's Chamber is built entirely from granite blocks, some weigh over 70 tons. The surfaces on those blocks are flat to within 1/1000th of an inch across several meters. That is not rough construction. That is precision. Above the King's Chamber, 5 more chambers sit roofed with granite beams, each weighing approximately 70 tons, shaped and fitted with accuracy that makes modern structural engineers go quiet when they calculate what producing it would actually require. At the Valley Temple at Giza, granite sections are joined so tightly that a razor blade finds no gap between them. Statues carved from single granite blocks carry surface details so refined that early engineers who examined them used the word machined. Not impressive, not skillful, machined. That was the standard they were comparing it to. Then there are the drill cores. At ancient Egyptian sites, drill cores pulled from granite show spiral grooves cut into solid stone. The feed rate those grooves imply, meaning how fast the drill moved downward through granite per rotation, made manufacturing professionals set down their calculations and stare. The grooves are consistent, geometrically clean, and they descend at rates that copper tools loaded with sand cannot come close to matching. I find that detail particularly hard to argue away. The grooves are physically there. The geometry is measurable. It either matches the proposed method or it does not. Now here is what mainstream archaeology had been saying about all of this for over 100 years. Copper saws, sand as an abrasive, and dolerite stone pounders. That was the complete official explanation. And the problem is not that it was unpopular. The problem is that basic material science does not support it. Copper sits at roughly 2.5 to 3 on the Mohs scale. The quartz in granite sits at 7. When you try to cut a material rated 7 using a tool rated 3, even with an abrasive in between, the tool destroys itself before the stone meaningfully yields. That is not an opinion. That is basic material science. It was basic material science long before anyone applied it to ancient Egypt. Controlled experiments confirmed this problem. A researcher at the University of Manchester spent years running laboratory tests of copper tools loaded with sand against granite. He wanted to prove the conventional explanation was correct. The data he got back was embarrassing to that explanation. progress measured in fractions of a millimeter per hour. Copper tools degrading rapidly. Cut surfaces that were rough and uneven, looking nothing like the smooth, precise surfaces found at ancient sites. He acknowledged openly that the experiments raised more questions than they answered. Not new questions. The same questions that were always there, now with hard numbers confirming something was fundamentally wrong with the standard account. Dolerite pounders work in a very narrow sense. Percussion can chip away at hard stone slowly, but the pace is so slow that shaping even a modest granite surface requires hundreds of labor hours. Scale that to the king's chamber with its dozens of massive granite blocks, and the labor calculation becomes enormous. And percussion still does not explain the precision. You do not get surfaces flat to 1/1000th of an inch by hitting rock with rocks and soft metal. That precision gap was always there. For decades, the official explanation simply did not address it. To me, this is the part I find genuinely strange. The gap between what the copper and sand theory predicts and what the actual surfaces show is not small. It is enormous. Engineers who examined these surfaces firsthand did not say pretty good for primitive tools. They said the tolerances matched or exceeded modern manufacturing standards. That is not a minor discrepancy. That is a complete mismatch. And it sat in plain sight for 100 years, while the same answer kept getting repeated in textbooks and museums. Now here is where the evidence actually changes. In 2022, a materials scientist specializing in tribology, which is the study of friction, wear, and lubrication, ran tests on ancient Egyptian granite artifacts that had never been run before. He used a scanning electron microscope and energy dispersive X-ray spectroscopy. These tools reveal surfaces at the molecular level, detail completely invisible to optical microscopes. Invisible to every researcher who had examined those same surfaces across the previous century. He had no background in Egyptology, no stake in defending or attacking any explanation. He was a specialist examining evidence with the most precise instruments available to modern material science. He expected to find sand particles and copper residue. That is what 100 years of Egyptology said he would find. What the scan showed was completely different. The wear patterns were wrong for sand. The scratch profiles did not match sand abrasion at all. And when he identified what was actually embedded inside those 4,000-year-old cutting grooves, the finding was striking. Corundum, aluminum oxide, a mineral that rates at 9 on the Mohs hardness scale, just one step below diamond on the entire scale. In nature, corundum is the mineral that forms rubies and sapphires. In industry, corundum is one of the most widely used abrasive materials on Earth. It cuts, grinds, shapes, and finishes the hardest engineering materials known. It is used in grinding wheels, abrasive papers, and precision polishing compounds across aerospace and manufacturing every single day. And it was sitting embedded inside cuts made 4,000 years ago, inside grooves that every Egyptologist in the world had examined and assumed contained nothing more unusual than ordinary desert sand. What I understand now is why this matters so much. Corundum does not occur naturally in Egypt in any form suitable for industrial use. The nearest significant deposits are in trade regions that ancient Egypt did connect with through long-distance exchange networks. So finding corundum in ancient cutting grooves means several important things at once. Someone had to know what corundum was. Someone had to know where to get it. Someone had to know how to process it, how to grind it to the right particle sizes, how to mix it with a liquid carrier to form an effective abrasive slurry, and what consistencies worked for different cutting applications. That is not an accident. That requires systematic material knowledge applied deliberately and refined over time. The researcher who ran these scans said this directly. Using corundum effectively requires understanding mineral hardness at a genuinely sophisticated level. You have to test. You have to refine. You have to optimize through repeated experimentation. That process is, in every meaningful sense, the practice of material science. Applied 4,000 years before anyone had coined a name for the field. After the microscopic finding came controlled experimental trials. A workshop, granite blocks, copper tools, and 3 abrasives, tested head-to-head under fully documented conditions. Sand, quartz powder, and a corundum quartz slurry. The results were not close. Sand produced approximately 0.5 millimeter of cutting depth per hour. Tools degraded fast. Cut surfaces were rough and uneven. Quartz powder did marginally better, about 0.8 millimeters per hour, still completely inadequate to explain ancient precision surfaces. Then they loaded copper with the corundum quartz slurry, over 3 millimeters per hour, 6 times faster than sand. The copper tools lasted dramatically longer. The cut surfaces were smooth, clean, and geometrically accurate. A 6-to-1 difference in cutting speed is not marginal. It changes the entire scale of what becomes possible. Then came the drilling tests. The corundum slurry produced core samples with spiral grooves that matched the exact pattern found in ancient Egyptian drill cores, the same grooves that had confused manufacturing engineers for decades, the same grooves that copper and sand experiments had never reproduced under any conditions. Right there in a modern workshop, using ancient tool geometries and the recovered abrasive, those mystery grooves appeared fresh in modern granite. That is experimental replication, not a theory about what might have worked, an actual demonstration that it does work, producing results that match the physical evidence left in ancient stone. A professional stonemason with decades of commercial granite work was present during those drilling tests. He described the change as immediate and unmistakable when the slurry switched to corundum. The copper stopped fighting the granite and started guiding the abrasive. The cut went smooth. The speed jumped. The tool wear dropped. He said it was the first time in his entire career that he could physically see, in real time, how the ancient method actually worked. The experiments also revealed something worth understanding clearly. Working with corundum slurry demands real skill. Too thin, and it loses cutting power. Too thick, and it clogs the groove. Pressure has to stay consistent. Feed rate has to be controlled. Every variable matters, and the margin for error is narrow. This was not something you hand to unskilled labor. It required craftsmen who had spent careers refining their technique, knowledge passed from master to apprentice across generations. That tells us something important. These were not primitive workers improvising with whatever was available. They were maintaining and transmitting a specialized craft, tradition, built on deep material knowledge accumulated over time. Now, I want to be honest about what is still open here. The microscopic finding of corundum in ancient cutting grooves is confirmed by laboratory analysis. The experimental replication showing corundum slurry produces matching results at 6 times the speed of sand is confirmed by the workshop trials. Those are 2 independent lines of evidence pointing the same direction. What remains as legitimate open questions is this: how much corundum would large-scale granite cutting have required across the full construction timeline? Is there direct archaeological evidence of corundum entering Egyptian trade networks during the relevant dynasties? Could the traces in those ancient grooves represent later contamination rather than original use? These are fair questions. Good science asks them. The evidence so far points strongly in one direction, but those questions need continued investigation. What I take away from all of this goes beyond just the corundum finding. The basic test, pointing a scanning electron microscope at 4,000-year-old cutting grooves to identify what was actually inside them, had never been done in a century of examining these surfaces. The instruments existed. The laboratories existed. The granite artifacts sat in accessible collections and at ancient sites. Nobody ran the test because the answer was assumed to be already known. That is a significant failure, not of any individual researcher, but of the kind of curiosity-driven investigation that good science depends on. The surfaces preserved the evidence the entire time. They were simply never examined with tools capable of reading it. If corundum-based abrasive slurries were the method ancient Egyptians used to cut granite at those precision levels, the technological picture of ancient Egypt has to be substantially revised. They understood mineral hardness at a sophisticated level. They maintained organized supply networks to source an industrial material unavailable locally. They developed and standardized processing techniques for that material across generations. They sustained specialized craft knowledge through structured transmission from skilled practitioners to trained apprentices over the full span of construction. That is a significantly more advanced technological profile than copper, sand, and patience implies. Not advanced in a mysterious sense, advanced in a practical, systematic, deeply skilled sense. 3 independent lines of evidence now converge on the same conclusion. Microscopic analysis found corundum in ancient grooves. Experimental replication confirmed corundum slurry produces matching results at 6 times the speed of sand. And basic material science explains exactly why corundum works, where copper and sand cannot. The secret of how ancient Egyptians cut granite with that level of precision is most likely not a mystery anymore. So for me, the main thing is this. The ancient Egyptians were skilled practitioners of a sophisticated craft, using carefully sourced and processed materials, producing results that match precision manufacturing standards. That is what the granite shows. That is what the corundum confirms. And the stone preserved that evidence for 4,000 years, waiting for someone to finally point the right instrument at it and actually look.